Okay, and so when we talk about decision trees, a lot of this is connected to the concept, the basic concept of counting, if you will, and what we define as the expected value. Okay, so when you think about a mean, okay, a mean in essence is an expected value, right? And so it is called an expected value because it's an expectation out of multiple different numbers. If I have 2, 3, and 4, if I ask you what's the mean, you'll say, Dr. B, it's 3. And I ask you, how did you get that? And you say, well, all I did was I added up those numbers, I divided by 3, and I get 3. And therefore I ask you, why should you divide by 3? Why can't you just add them and just say, that's my mean? Why couldn't you multiply them and say that's my mean? What makes you say that you have to add them up and divide by 3 to understand that it's a mean or an expected value? And therein lies the basic idea of probability. So in essence, you have 3 events here: event 1, event 2, and event 3, right? So the first event has a value of 2, the second event has a value of 3, the third event has a value of 4. And therefore, anytime you choose 2, the probability of choosing 2, or that specific event from 3 events, is 1/3. The probability of choosing 3 out of those 3 events is 1/3. The probability of choosing 4 out of those 3 events is 1/3. So all you are doing is you are taking the products of those and adding them up. In other words, for each event, you are looking at the event's magnitude, which is the value of 2, and its probability. The event's magnitude and its probability. The event's magnitude and its probability. And you are doing the sum product of them to find the overall expected value. That's how it is done. If I do a weighted average, these weights will change. In a regular average, it's equally weighted, which is why average is extremely motivated by outliers. Because if this value was 20, then the average is pushed up because every one of them have equal weights. They're equally important in the expectation. Sometimes it's not. So that backdrop is very important in the understanding of decision trees. And let's do a very, very simple example here. A building supply store is considering expanding its capacity to meet a growing demand for its products. The alternatives are to build a new store at a site nearby, expand the old one, or do nothing. Here are the regional outlooks from economics perspective. 60% chance that the economy will remain unchanged, 20% probability of an upturn, 20% chance of an economic downturn. And then some estimates of annual returns have been provided. So if you're building a new store and if your market has an upturn, then you will have your expected profit or return of 1.9 million bucks. If you are expanding an old store and you have a stable market, then you will have $500,000. If you are doing nothing and if you have a market downturn, then you are losing 100 grand. And that's how this matrix is set up. Okay, so before you set up a decision tree, the one thing that I want to always tell my students is to understand what are my alternatives. Okay, and oftentimes I see students writing up alternatives in this way: upturn, downturn, unchanged. You know why this is wrong? This is wrong because these are alternatives that you don't have any control on. Okay, so when you talk about alternatives, alternatives are stuff on which you have control on. Those are your options that you can choose. So your options are to either build, expand, or do nothing. Okay, so if this is you and this is where you start, you have not made a decision yet, you have 3 options in your hand. Either you build, either you expand, or you do nothing. Now for each one of these options, you now have 3 economic possibilities. One is an upturn, one is a stable market, the other is a downturn, right? The chance of an upturn is 0.2. The chance of a stable market is 0.6. And the remaining 0.2 is definitely the chance of a downturn. Now, if you are trying to build a new store and if the market is an upturn, what is your net outcome? 1.9 million. If you are trying to build a new store and the market is stable, your outcome is 0.3. If you are trying to build a new store and you have a downturn, then your overall outcome is 0.5, negative, or a loss of 0.5. So now, what is the overall expected value of your profit if you want to build a store? What is your expected profit from this outcome? That's where this concept comes back to use. So in other words, if you go this route, this is your outcome with a probability of 0.2. This is your outcome with a probability of 0.6. This is your outcome with a probability of 0.2. So your overall expected value, if you build, would be 1.9 times 0.2 plus 0.3 times 0.6 minus 0.5 times 0.2. Same idea. Magnitude, likelihood. Magnitude, likelihood. Magnitude, likelihood. Okay? Value, probability. Value, probability. Value, probability. You take that sum product and that becomes your expected value if you want to build a new store. You do the same exact analysis with the calculations here based off of these numbers. You do the same exact thing with the calculations here based off of these numbers. And then you find an expected profit from expanding, a profit from doing nothing. So now, standing here, you have three options and you have been able to figure out the overall expected profit from each of those options. Okay, so expected profit from building a new store, expected profit from expanding, and the expected profit from doing nothing. You have those dollar values. What should you do? In this case, you are trying to maximize your profit, so you choose the number between these, that is the max, right? You choose the maximum value, and that's the direction that you should go in terms of your decision. If this was about costs, okay, this is how much this thing will cost, okay, so you would then in that case choose the minimum value of those outcomes because you want to minimize cost. If this was the amount of time it takes to build a new store in different market conditions, if it was time, again you want to choose the option that takes the least time, which is where the idea of minimum comes. So that in short is an idea of decision trees.